March 1st, 1982. A picture is arriving from another planet, and it is arriving very slowly, one vertical line at a time, a stream of numbers ticking in from a machine that is currently sitting inside an oven. The machine is a Soviet lander called Venera 13. It is standing on the surface of Venus. The air around it is 462 degrees Celsius. The pressure pressing against its shell is close to 90 times what you feel at sea level on Earth. Every component inside it is failing on schedule, exactly the way the engineers expected it to. It has 127 minutes. And in that time, it does something no machine had done before, and no machine has done since. It takes a color photograph while standing on the surface of Venus. Then, the relay carrying the signal drifts out of range, and the transmission stops. 4 days later, its twin does the same thing and manages 57 minutes. And that is the end of the record. 44 years have passed. Nothing has photographed that ground again. A handful of panoramas from 2 spacecraft, taken across 2 afternoons, are still the first and still the only color images humanity has of the surface of the planet next door, which makes the real question a strange one. Because we have been staring at the same few frames for 4 decades, reprojecting them into views no camera ever took, arguing about the shapes buried inside them, and some of what people are convinced they can see in those pictures was never there at all. So let's look at them properly. Venus is the closest planet to Earth, and for most of human history, it was also the least visible. That sounds like a contradiction. It isn't. Venus is wrapped in an unbroken deck of cloud made of concentrated sulfuric acid, sitting on top of an atmosphere that is 96.5% carbon dioxide. From outside, the planet is a smooth, featureless, pale sphere. There is no surface detail to see. There never has been. Point the best telescope on Earth at Venus, and you get a blank disk. Which means that until 1975, no human being had any idea what the ground on Venus actually looked like. Not a guess, based on a blurry image. Nothing at all. Now, the Soviet Union decided to solve this problem the hard way. Between 1961 and 1984, the Soviet space program sent 16 probes toward Venus. The early years of that campaign are close to a straight list of failures. Spacecraft that never left Earth orbit, spacecraft that went silent on the way, landers that stopped transmitting during descent. But the failures kept getting further along the timeline. In 1966, Venera 3 became the first spacecraft to reach the atmosphere of another planet. In 1970, Venera 7 achieved the first successful soft landing on the surface of another world. Not on Mars, not on the Moon. On Venus, the single most hostile piece of real estate in the inner solar system. And that is where the engineering problem became genuinely strange, because the Soviets were not trying to build a spacecraft. They were trying to build a diving bell that could survive being dropped into a furnace. The man who had to solve the specific problem of taking a picture in that environment was A.S. Selivanov, working with his team at the Institute of Space Device Engineering. His constraint was simple and brutal. He could not put a camera on the outside of the lander. Heat and pressure would destroy it in seconds. He also could not put a camera behind a normal lens, because the optics would not survive either. What he built instead is one of the more elegant pieces of improvisation in the history of spaceflight. The camera sits inside the pressure vessel, protected by the same shell that keeps the electronics alive. Light from outside enters through a small, specially designed porthole, gets routed through a periscope, and only then reaches the imaging system. The camera never touches Venus. It only looks at a reflection of it, and it does not take a picture the way a phone takes a picture. It scans. A mirror sweeps back and forth, building the image line by line, sending each line to Earth as it goes. That detail matters more than it sounds like it does. Hold on to it. We will come back to it. October 22nd, 1975. Venera 9 lands on a slope at roughly 31 degrees north latitude on the daylight side of the planet. Before that moment, there were serious scientific predictions about what the cameras were going to see, and most of them were pessimistic. One school of thought held that the atmosphere of Venus was so dense that it would bend light severely, that the horizon would curve upward, that the landscape would wrap around the lander like the inside of a bowl, and that the camera might end up photographing parts of the spacecraft itself through the distortion. Another school of thought held that the surface would simply be lost in haze, thick, soupy, orange fog, nothing visible past a few meters. Both of those predictions were reasonable. Both of them were wrong. The panorama that came back showed a rocky hillside, flat, sharp-edged stones scattered across the ground, with clear separation between foreground and background, and a visible horizon. No fog. No bowl. No optical illusion. It looked, in a way that nobody was prepared for, like a place. That is the single most surprising thing in this entire story, and it deserves a moment. For decades, Venus had been treated as a kind of theoretical hell, a set of numbers about temperature and pressure with no picture attached. And then the first image arrives, and it is a landscape. Rocks with edges, shadows, ground that a person could describe with ordinary words. The most alien place we had ever reached turned out to be legible. It was also, technically, an awful image. And that is not a criticism, it is a measure of how difficult the problem was. The Venera 9 panorama was assembled from 517 vertical lines, each line only 115 pixels tall, 6 bits of brightness per pixel, plus one more bit to check for errors. A single sweep of the scanner took 30 minutes. In that half hour, telemetry from the lander's other instruments was cut directly into the middle of the picture, punching a blank column through the image because bandwidth from Venus was too precious to waste on redundancy. A second camera on the opposite side of the lander was supposed to double the coverage. It never opened. The atmospheric pressure was so high that it prevented the lens cap from ejecting. Venera 10 came down a few days later and returned almost 2 full scans of its own site. Same result. One meaningful difference: the terrain looked less like scattered rubble and more like solidified lava flows. Smooth, layered, poured. 2 landing sites, thousands of kilometers apart, and both of them said the same thing about the planet. This ground was made by volcanoes. Its second camera failed too. Now, both of those panoramas were black and white. The obvious next step was color, and that job went to Venera 11 and Venera 12 in December 1978. Here is what happened. Both landers survived the descent. Both reached the surface intact. Both operated for over an hour. Venera 12 lasted 110 minutes, one of the longest surface lifetimes of the entire program, and both of them were blind. The protective covers over the camera portholes failed to eject. Same category of failure that had cost them the second cameras on Venera 9 and Venera 10, now repeated on a mission where imaging was the entire point. 2 spacecraft, years of work, an interplanetary transfer, a successful landing on the hardest surface in the solar system, and not one photograph. That failure is the reason the pictures we are about to talk about exist at all. The engineers went back and redesigned the mechanism, and they got exactly one more chance to use it. Venera 13 landed on March 1st, 1982, in a region called Navka Planitia. Venera 14 landed 4 days later, on March 5th. This time, the covers came off. To understand what we are actually looking at in those panoramas, you have to understand what the camera was doing, because it does not work like any camera you have ever used. There are 2 of them on each lander, mounted on opposite sides. The opening of each camera sits about 90 centimeters above the ground, roughly waist height on a person. The optical axis is tilted 50 degrees down from vertical, so the camera is not looking straight out at the horizon. It is looking down and away, at an angle, the way you would look at your own feet, and then let your eyes drift outward. That tilt is doing something clever. It means the camera can resolve detail down to the millimeter scale in the soil immediately beside the lander, while still catching objects around 10 meters across out near the horizon, roughly 3 1/3 kilometers away. One instrument, two completely different scales of information. It also means the image comes out geometrically warped. If you correct the picture so that the horizon runs straight, the panorama stops being a rectangle. It becomes a shape bounded by two curves, like a slice cut out of a sphere. Almost every version of these images you have ever seen has been unwarped by somebody at some point using some assumption about the geometry. Hold on to that too. The scanning system on Venera 13 and 14 was a serious upgrade over the 1975 landers. Each panorama is 1,000 vertical lines, 211 pixels to a line, with an angular resolution of 11 arc minutes, about twice as sharp as the earlier cameras. The mirror takes 0.82 seconds to complete a single line. Each individual pixel is transmitted in about 3 1/3 milliseconds. A full sweep takes 13 minutes, and the brightness values are not stored the way a modern image stores them. Each pixel carries 9 bits of data, encoded on an approximately logarithmic scale, which is to say the camera was designed to compress an enormous range of light levels into a small number of values, the same way your own eye handles a dark room and a bright window at the same time. That decision is a large part of why these images survived at all. Nobody knew, in advance, how bright the surface of Venus was going to be. Now, the color. The cameras did not have a color sensor, they had glass filters. The scanner would sweep a full panorama with no filter, then sweep again with a red filter in place, then again with green, then again with blue. 4 different passes over the same landscape, minutes apart, from a machine that was slowly cooking. The unfiltered sweeps were bright and clean. The filtered sweeps were much darker, and therefore much noisier, because each filter throws away most of the incoming light. So the color information and the detail information ended up in separate images of different quality, which brings us to the actual color of Venus. The sky at both landing sites was measured directly, not guessed. Spectrometers on Venera 11, 13 and 14 recorded the light coming down from the zenith across wavelengths, from the near ultraviolet through the visible range and out into the infrared. And the answer is consistent. The sky over Venus is orange. Here is why sunlight entering the Venusian atmosphere has to travel through an enormous depth of dense gas before it reaches the ground. Blue light scatters far more easily than red light, the same physics that makes Earth's sky blue. But on Venus, the column of atmosphere is so deep that the blue light scatters away entirely before it ever gets down. What survives the journey is the red end of the spectrum. There may also be some additional component in the atmosphere absorbing blue light that has never been positively identified. So the surface of Venus is lit almost entirely by warm, filtered, sourceless light. And sourceless is the right word. The sun is not really visible from the ground. It is smeared across the entire cloud deck. The illumination at the Venera 13 site was measured at somewhere between 3 and 3,500 lux, comparable to a heavily overcast day on Earth, or a very well-lit room. Enough light to read by. There are no sharp shadows because there is no point source to cast them. Light arrives from the whole dome of the sky at once, which produces a small, quiet detail in the images that I find hard to stop thinking about. There are shadows in the Venera panoramas, but only directly underneath the lander itself, and only underneath objects sitting very close to the ground. Because the sky is the light source, the only way to make a shadow is to block a piece of the sky. The lander is casting a shadow made of the sky it is standing in front of. Now, the sky being orange has one more consequence that took decades to properly untangle. The rocks on Venus are not golden. They look golden in the images because everything at that landing site is bathed in orange light. but strip the atmospheric tint back out, which is exactly what researchers at Brown University did when they revisited the data with modern image processing, and the ground underneath is dark grey. Dark grey because it is basalt, volcanic rock, the same material that makes up the floor of the Pacific Ocean, and we do not have to infer that from colour alone because the landers measured it. Venera 13, Venera 14, and the later Vega 2 probe all carried X-ray fluorescence spectrometers, and all three returned a chemical breakdown of the rock they were sitting on. The results are genuinely strange in how familiar they are. The Venera 14 sample matches a specific class of terrestrial rock called tholeiitic basalt, and not just loosely. When the measurements were compared against a large database of ocean floor rocks from Earth, the closest matches came from the Kane Fracture Zone, a region of the Mid-Atlantic Ridge. Primitive, low-calcium, high-alumina pillow basalts, the kind of rock that forms where the ocean crust of our own planet is being made. The Vega 2 sample was different again, resembling altered gabbros or the basic lavas found in terrestrial intrusions. And Venera 13, sitting a few thousand kilometers away, returned something else entirely. Its chemistry is consistent with an alkali basalt, of the sort that on Earth is associated with deep partial melting of a carbon-rich source region far below the surface. The closest terrestrial analogues are places like the Loihi Seamount off Hawaii and the volcanic island of Tristan da Cunha in the South Atlantic. So what does that mean? It means that in the 4 hours of surface data humanity has ever collected from Venus, at sites separated by thousands of kilometers, we found at least 2 chemically distinct kinds of volcanic rock, which suggests that Venus is not a monotonous ball of one lava. It suggests that magma on Venus ponds at different depths cools, separates, and produces a range of compositions, the same fundamental process that gives Earth its variety of igneous rock. Some researchers go further and argue that Venus may be as compositionally diverse as our own planet. That interpretation is not settled. The error bars on those 1980s measurements are large by modern standards, and the landers could not determine the mineral structure of the rock, only its bulk chemistry. What we have is a strong hint from 3 points on a planet with the surface area of Earth. 3 points. That is the entire ground truth. Everything else we believe about the surface of Venus is built on top of it. And there is one more thing those 2 landers did that is almost never mentioned. They listened. Venera 13 and Venera 14 both carried instruments that recorded sound, which makes the Venera program the first and still the only program in history to transmit both pictures and audio from the surface of another planet. We have images of Venus, and we have the sound of the air moving across a machine standing on it. Now, think about what that air actually is. At the Venera 13 site, the atmosphere had a density of about 59.5 kilograms per cubic meter. Earth's air, at sea level, is a little over 1. So, the gas surrounding that lander was roughly 50 times denser than what you are breathing right now, dense enough that it starts behaving less like an atmosphere and more like a shallow ocean. That density is also why the wind on Venus is deceptive. It moves slowly. At the Venera 13 landing site, it was measured at about 0.5 meter per second, which on Earth would barely disturb a candle flame. But in a fluid that heavy, a breeze that gentle still carries real force. And it is enough to strip settled dust off a spacecraft over the course of an hour. Which brings us to the clock. Every one of these missions was a countdown from the moment of touchdown. Venera 9 lasted 53 minutes on the surface. Venera 10, 65 minutes. Venera 11, 95. Venera 12, 110, the longest of the whole program. Venera 13, 127 minutes of contact. Venera 14, only 57. The 2 Vega landers in 1985 managed about 20 minutes each, and they came down on the night side, so they took no pictures at all. But here is a detail that reframes the entire set of images. If you look at the raw Venera 13 transmission, the noise gets noticeably worse toward the end. The natural assumption is that you are watching the lander die, that the heat is finally winning, and the picture is degrading as the electronics fail. That is not what is happening. The main spacecraft that carried Venera 13 to the planet was on a flyby trajectory. It did not stop. It kept moving, relaying the lander's signal back to Earth as it went, and as it traveled further away, the link got weaker. The noise creeping into those final frames is the relay drifting out of range. The lander was still working. It was still scanning. It was still sending pictures of Venus into an atmosphere that nobody was listening to anymore. We did not stop receiving images because the spacecraft stopped taking them. We stopped receiving them because we left. Now here is the part of the story that almost nobody talks about, and it is the part that changes how you should look at every one of these pictures. The image you have seen of the surface of Venus is not the image the Soviets released. Remember that each lander scanned its surroundings repeatedly. Venera 13 did not take one panorama. It took a whole sequence, clear sweeps and filtered sweeps, over and over, for 2 hours. And every one of those sweeps was transmitted to Earth twice, once live, relayed through the flyby spacecraft as it happened, and once more replayed later from a tape recorder on board. Every copy is damaged in a slightly different way. Different dropouts, different noise, different interference. The published Soviet panoramas were mosaics, the cleanest sections of several transmissions, stitched into one coherent view. In the 2000s, an American researcher named Don Mitchell went back to the original digital telemetry. He obtained the raw data through contacts in the Russian science community, and he began rebuilding the panoramas from the ground up. His approach was to stack the multiple transmissions of the same scan against each other to cancel out the noise, then apply the camera's published photometric calibration to convert those logarithmic brightness codes back into true linear brightness. Then he solved the color problem the way a broadcast engineer would. Take the sharp, low-noise detail from the unfiltered sweeps. Take the color information from the darker, noisier filtered sweeps and combine them in a color space that keeps the two separable. The result is dramatically better than the originals. Detail appears in the deep shadows. Detail appears in the bright areas that were previously blown out. The shape of the rocks becomes readable. He then went one step further and remapped the spherical panoramas into perspective projections, reprojecting the data as though you were standing at the lander, looking outward, or hovering above it, looking down. Those perspective views are the images that went around the world. And in 2021, one of them went viral on social media, captioned as the only clear photograph ever taken from the surface of Venus. Millions of people saw it. It was shared as a raw photograph from a Soviet spacecraft. When journalists tracked down its origin, Mitchell confirmed he had produced the underlying monochrome reconstruction himself. The colorized version circulating online had been made by other people afterward, and in his assessment, those colors were not particularly accurate. Nothing dishonest happened here. This is normal, careful, high-quality scientific image processing, and it is documented in detail. But it does mean something specific, and it is worth saying plainly. What the public thinks of as a photograph of Venus is a reconstruction. It is a defensible, well-argued reconstruction built from real telemetry. And it is still a set of choices about how to turn 9-bit numbers from 1982 into something a human eye can interpret. Which brings us to the strangest chapter of all. Because if you stare at reprocessed images long enough, you start to see things in them. Leonid Xanformality was not a fringe figure. He joined the Space Research Institute in 1968. He designed instruments for the Mars 3 through Mars 7 spacecraft. He worked on infrared and ultraviolet imaging of the Venusian cloud structure during the Venera 9 and 10 missions. The sensors he built for Venera 11 through 14 produced the first detection of lightning storms on Venus. By any measure, he was one of the most accomplished planetary scientists of the Soviet era. Starting around 2012, he began publishing papers arguing that the Venera panoramas contained living organisms. His method was sound in principle. Instead of studying the single published mosaic from each site, he compared the individual sequential panoramas against each other, looking for objects that appeared, disappeared, or changed shape between sweeps. That is a legitimate thing to do. Nobody had systematically done it. What he reported finding were objects he gave names to. A structure near the Venera 13 lander he called the Scorpion, roughly 15 to 17 centimeters long, which was absent in the early panoramas, emerged gradually from disturbed soil over the course of about an hour and a half, and was gone by the 119th minute. A dark object near the soil testing cone that was present in the first 13 minutes and vanished from every later frame. A shape at the Venera 14 site he called an amesada, which he compared to a lizard and which appeared to shift position by 1 or 2 centimeters over 90 minutes. A large, jagged, radially structured object in the Venera 9 data, about 1.5 meters across, sitting above the ground with a shadow beneath it. He proposed that these were extremely slow-moving organisms built from some non-aqueous medium moving at speeds under 1 millimeter per second. Now, the counter-argument is comprehensive, and it is important to walk through it because this is exactly the kind of claim that gets stripped of its context and repeated forever. First, the noise. The successive Venera transmissions used 2 different methods of modulating the radio carrier signal, and each method produced a different noise signature. Compare pixel values between 2 versions of the same panorama, and you do not get a clean match with a few moving objects. You get a broad scatter of differing values across the entire frame. Almost all of the difference between those images is noise, not landscape. Second, the processing. Xan Formality stated that no retouching was performed, but the papers also describe filling in missing regions from other frames, adjusting contrast and brightness, and applying blur and sharpen operations. Sharpening a noisy image is precisely the operation most likely to manufacture crisp-looking structure out of nothing. Third, and most simply, the landing itself. These spacecraft hit the ground hard. Venera 13 came down at around 7.5 meters per second, crushed the soil beneath it to a depth of several centimeters, and threw material sideways. Dust settled on the lander and was then gradually blown off by the wind over the following hour. Don Mitchell noted exactly that effect in 2 Venera 13 frames taken an hour apart, showing soil clearing off the landing ring. A ditch appearing in disturbed soil, lengthening, and then resolving into a shape is what you would expect from ejected material settling around an obstacle in a wind of about 0.5 meter per second. The planetary science community did not accept the interpretation. The most widely read response, from Emily Lakdawala, concluded that the images had been processed so heavily, on top of so much noise, that micro-analyzing individual features was not a meaningful exercise. So the honest position is this: there is no evidence of life on the surface of Venus. There are a small number of low-resolution, heavily processed images taken by 4 spacecraft over a combined total of a few hours, 44 years ago, and there is no way to go back and check. That last part is the real anomaly, not the Scorpion. The fact that a claim like this can be made about another planet in our own solar system, and the only available response is an argument about image processing, because nobody has photographed that ground since. So, if we cannot photograph Venus, how do we see it at all? We stopped using light. We started using radio. Between 1990 and 1992, NASA's Magellan spacecraft mapped Venus with synthetic aperture radar, a technique that fires radio waves at the ground and reconstructs an image from the echoes. Radio passes straight through sulfuric acid cloud as though it were not there. Magellan mapped 98% of the planet at a resolution somewhere between 100 and 300 meters, And more than 30 years later, those maps are still the best global picture of Venus that exists. No later orbiter has matched their coverage. But radar is not photography. It does not record color or light. It records how strongly a surface bounces a radio wave back at you, which depends on roughness, on slope, on the angle you happen to be looking from. Magellan flew its survey in 3 separate passes, called cycles, and it looked in different directions on different cycles, east looking on the first, west looking on the second. About 42% of the planet ended up imaged 2 or more times from different angles, which created an opportunity that sat unused for 30 years. If you have 2 radar images of the same place, taken months apart, then anything that changed in between is recorded in the difference. In the early 20s, a research professor at the University of Alaska Fairbanks named Robert Herrick decided to go looking. NASA had just selected a new Venus orbiter, and that selection is what prompted him to open the archive. He spent roughly 200 hours manually comparing Magellan images of different orbits by eye, one region at a time. He has said openly that he did not expect it to work. Then he found a volcanic vent on the flank of Mont Mons, near the equator, that had been imaged twice in February 1991, and again in October 1991. In February, the vent is nearly circular, with steep interior walls covering an area of about 2.2 square kilometers, less than 1 square mile. 8 months later, it has roughly doubled in area, lost its circular shape entirely, become shallower, and appears filled to the rim. Now, the 2 images were taken from opposite viewing angles, which makes them genuinely difficult to compare. A pit can look completely different depending on which side the radar is illuminating it from. So Herrick worked with Scott Hensley at NASA's Jet Propulsion Laboratory to build computer models of the vent in a range of geometries, simulate how each model would appear under both viewing conditions, and test which scenarios could reproduce what the radar actually saw. They modeled landslides, they modeled collapse, they varied the depth, the wall steepness, the local terrain slope. Only volcanic activity fit. Downhill of the vent, the second image also shows radar-bright material covering about 69 square kilometers, consistent with fresh lava flows, and comparable in scale to the 2018 Kilauea eruption in Hawaii, which covered around 35 square kilometers. A second team, led by Davide Sulcanesa in Italy, later took the same approach to a different signal. Instead of looking for shapes that changed, they looked for places where the strength of the radar return increased between 1990 and 1992, the fingerprint of new rock forming on the surface. They found it in 2 regions, the volcano Sif Mons and the western part of Niobe Planitia. After ruling out wind-blown sand and atmospheric interference and checking the flow paths against topography to confirm the material behaved like a fluid running downhill around obstacles, they estimated new lava deposits between 3 and 20 meters deep, covering about 30 square kilometers at Sif Mons and about 45 square kilometers at Niobe Planitia. For scale, enough rock to fill roughly 36,000 Olympic swimming pools at one site and 54,000 at the other. The 2022 eruption of Mauna Loa produced enough to fill about 100,000. So the comparison is direct, and it is not exotic. Venus erupts at roughly the rate that Earth erupts. But it is worth being precise about what that does and does not establish. Herrick's survey covered only about 1.5% of the planet's surface in the regions considered most likely to be active. One changed feature was found. That is enough to prove Venus is geologically alive today. It is not enough to say how alive. And the low detection rate does tell us that Venus is far less volcanically active than Io, the moon of Jupiter, where over 100 active hotspots have been imaged. Then, in 2026, the archive gave up something else. A team led by Lorenzo Brazzone at the University of Trento was studying chains of collapse pits, lines of circular depressions that run for hundreds of kilometers across the Venusian surface. Most of them behave predictably in radar. A steep-walled pit produces a bright return that hugs the rim and stops there. One pit, on the western flank of Nix Mons, a shield volcano about 362 kilometers across, did not. Its echo included a bright streak that extended well past the rim, paired with a deep shadow beside it. That combination bright return where the beam has entered something, shadow where a roof has fallen in, is the same signature that lava tube skylights produce on Earth. The interpretation is that the pit is not a pit. It is a hole in a ceiling. From the length of the radar brightening and the size of the shadow, the team estimated the shape of the void underneath. The conduit is roughly 1 kilometer wide. The roof over it is at least 150 meters thick. The empty space below rises at least 375 meters. The radar signal traveled at least 300 meters into the tunnel before scattering back. That is a natural cavern wide enough to swallow a city block, tall enough to hold a skyscraper, sealed under a rock ceiling half again as thick as the Eiffel Tower is tall. For comparison, the famous lava tubes on Earth, Cueva de los Verdes on Lanzarote, for instance, are a few tens of meters across. Based on the slope of the surrounding terrain and the alignment of the neighboring pits in the chain, the full system may run for something like 45 kilometers beneath Nix Mons. That part is inference, not measurement. Only the section nearest the opening is confirmed. The other pits in the same chain do not show the signature, which may simply mean their entrances are choked with collapse debris. The formation process itself is straightforward, and it happens on Earth constantly. Fast-moving lava develops a hardened crust on top, while molten rock keeps flowing underneath. When the supply drains away or the flow changes course, the channel is left hollow. The proposed reason Venusian tubes can be so much larger is that lower gravity and a much denser atmosphere may let those crusts form faster and thicker, so wider roofs stay standing instead of falling in. That is a hypothesis. It fits the observation. It has not been confirmed, and the researchers themselves note that tube size probably depends on local conditions rather than some planet-wide rule. And all of this, the eruption, the lava flows, the cavern, came out of data collected before 1993. There are missions coming. NASA has selected two: Veritas, an orbiter built to map the surface in 3 dimensions with a new generation of radar and to identify what the rocks are made of using infrared windows in the atmosphere, and Da Vinci, a probe designed to fall through the air and analyze it on the way down. The European Space Agency is preparing Envision, which carries a subsurface radar sounder intended to look several hundred meters underground, which is, not by coincidence, roughly the depth of the Nix Mons tunnel. India is finalizing an orbiter of its own. The plan is for these spacecraft to work together. Veritas maps globally at high resolution. Envision goes back to anything interesting and looks closer. Da Vinci samples the air. If they fly as intended, the 2030s become the decade of Venus. And there is a real question they are being sent to answer. Venus and Earth are nearly the same size, nearly the same mass, nearly the same bulk composition, and nearly the same distance from the same star. Venus sits at the edge of what we would call the habitable zone. Past missions have detected granite-like rocks on its surface, and granite, on Earth, requires abundant water to form. There is a serious argument that Venus may have had liquid water on its surface for around 2 billion years. If that is true, then for a long stretch of solar system history, Venus was the most Earth-like world we have ever known about. And then something happened. The water went. The carbon dioxide stayed. The greenhouse effect ran away from the planet and never came back. And today, the surface is hot enough to melt lead. Every impact crater on Venus formed within the last 700 million years, which implies the entire surface was resurfaced by some global event before that. We do not know what that event was. Venus has no plate tectonics. It has no magnetic field. It rotates so slowly that a single day and a single night each last about 58 Earth days, and its year is not much longer than 2 of its own days. It is the closest planet to us. It is the most similar planet to us, and it took a path we do not understand and cannot yet rule out for ourselves. So here is where we actually stand. We have 4 black and white and color panoramas from 3 landing sites. We have chemical analyses of 3 patches of rock. We have a global radar map from a spacecraft that stopped working in 1994, which is still, in 2026, the best map that exists. We have a handful of eruptions caught by accident in 30-year-old data by people willing to spend 200 hours looking at it. We have 1 confirmed hole in the roof of 1 cave. Total time a human machine has spent looking at the ground on Venus. A little over 4 hours, spread across 2 afternoons 7 years apart, in 1975 and 1982. And in those 4 hours, the only reason we saw anything at all is that a group of engineers refused to accept that a camera could not survive there. They put it behind a periscope. They pointed it at the ground at an angle. They wrote the brightness down as logarithms because they had no idea how bright it would be. They scanned 1 line at a time for 13 minutes, while the machine around the camera slowly cooked to death, and they sent every line home twice in case 1 copy was lost. It worked, twice. Then the light went out of the images as the flyby spacecraft drifted out of range, the transmissions ended, and Venus closed again. We have been looking at the same few pictures ever since, sharpening them, recoloring them, arguing about the shapes inside them, reprojecting them into views no camera ever took, trying to squeeze a planet out of a few thousand pixels. And the honest truth is that we do not know what most of Venus looks like. We know what a hillside looks like at 31 degrees north. We know what a lava plain looks like near the equator. Everything else is an echo and a very good guess. There is a world sitting 40 million kilometers away, roughly the size of our own, with a sky the color of a slow sunset, and mountains we have never seen, and caverns we have only heard the shape of. And for 2 hours in 1975 and 2 hours in 1982, it let us look at it. We have not been back since.